right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 391. They are working on my building, so you might hear some drilling. They're doing work on the facade. I'm not sure what they're doing, but hopefully it's not too distracting. We need to forge ahead. We're in the home stretch. So by the end of this week, we'll have finished everything for the course. So let's not waste any time. Let's get into it. We do have, as I recall, a problem to finish from the last class, which was this guy. And hopefully you guys attempted that. And because, it's going to be on the test on this week. So you guys should know how to deal with series solutions to ODEs. This is one of the things, both at ordinary points and regular singular points. So hopefully you're getting the practice in, and hopefully it's going well so far. Let's actually just jump into this now. Let me move this chat box out the way, and let me just make a note that we started here, started from the bottom, started here on 7/13 day. Okay, and let's jump into it. So you got stuck by finding the recursive relation. Okay, let's see how far we can get here. So it says show that x naught equals 0 is a regular singular point. Compute the recursion formula for the coefficients associated with the larger root of the initial equation, and compute a1 and a2 when a0 is 1. Okay. So first we need to show x naught equals 0 is a regular singular point. X naught equals 0 is a singular point since it makes P of x equals 0. So remember, P of x was what we called the coefficient of the y double prime. We did that somewhere. We did that somewhere. Yeah, here. Anything that makes that function 0, we call that a singular point. If it's regular, it means that it obeys these two limits, which means that we can look at it in some sense as some kind of degenerate Euler equation, which we introduced last time. So to see that it's regular, you need to check two limits. You need to check the limit as x approaches 0 of x minus 0 times q over p. We also need to check the limit as x approaches 0 of x minus 0 squared times r over p. Okay, so in this case, our q is 2, so it's 2 over 3x. So this is the limit as x approaches 0 of x times 2 over 3x. So this is 2/3, which is finite. Yeah, so Faiz, I think you came in a little bit later, but yes, as I mentioned, they are working on the building out, so there is drilling going on outside. I don't know what they're doing. But yeah, hopefully it's not, hopefully you can hear me better than the drill. But we're just going to continue. So that's 2/3, so that's finite, which is good. Now, if I look at the r over p, that's x plus 5 over 3x. So this would be the limit of x squared times x plus 5 over 3x. If we look at that, yes. So this will cancel into that. So this just becomes the limit of x squared plus 5x over 3 as x is approaching 0. So that is 0, which is again finite. So this means x not equals 0 is a regular singular point. Okay, and we did tons of examples like that last week. Probably too much, in fact. Let's move on to the next part, compute the recursion formula. So now we know how we actually do that. So the assumption is we're going to assume y equals the series of a n x to the n plus r. And let's do the one where we don't have to really worry about coefficients, the index. And also we know that the initial equation is, well, we go to our original equation and we see pretty much so we're going to go to our original equation. Since we have this, what we would do is we would multiply through by an x, because I want the first term to look like a quadratic. Then I'd look who actually falls out of line with an Euler equation. That guy is okay, but both of these will not work in an Euler equation because these guys should be constants. So now the initial equation would look like 3r times r minus 1 plus 2r equals 0. So this is 3r squared minus r equals 0. So this means that r times 3r minus 1 equals 0. And so here you'd have r equals 0 or r equals a third. And this guy here is the larger root. So we're going to use that guy later. Okay. Now in the ODE, where do you use it? If I have 5xy instead of x plus, then no. So the 5x is one term, and it's not a constant term. So if you had something like 3x squared y double prime plus 2xy prime plus 5x times y, something like that, then no, you would ignore that whole term because the coefficient is a linear coefficient, right? If you had something like 3x squared y double prime plus 2xy prime plus something like 5x plus 3y equals 0, then that would actually distribute into 5xy plus 3y, and this one is okay, and that one is not okay, and so you'd ignore that part and leave the 3. Right? You keep the parts that make it look like an Euler equation. Okay, so now we're going to go into the ODE. We're going to plug these guys in. So I'm going to have 3x squared times n plus r times n plus r minus 1 an x to the n plus r minus 2. That is my y double prime. Plus, now I'm going to have 2x times n plus r an x to the n plus r minus 1. Then I'm going to have x plus 5. Then I'm going to have x plus 5 and x to the n plus r. Okay, that looks like everything. Actually, it should, I'm looking at the new equation, so it's like x squared plus 5x. Okay, yes. So x squared plus 5x. I'm scrolling back up and down. My eyes wandered to this part. So I'm plugging into this part because it's nice to have the x squared in the front because it's going to bump up that -2 in the power of the first term to become n plus r right away. So I'm plugging into this equation right here. All right, so now what would we get? Well, we would have the series. Well, for this one, I would do a, well, let's do this first. So I would have the series of 3 times n plus r times n plus r minus 1 a n x to the n plus r plus the series of 2 n plus r a n x to the n plus r plus, here I would have the series of a n x to the n plus r plus 2 plus the series of 5a(n) x to the n plus r. These problems are too long and keep running into the chat box. Plus 1 equals 0. Okay, so for the last two, I'm actually going to do like a shifting here. So for this one, I would do shift all n's to n minus 2's. So this guy I would shift to become a n minus 2 x to the n plus r. This guy I would shift all n's to n minus 1's. So this guy would become 5a(n) minus 1 x to the n plus r. And then I would be able to do one big series where I put all these guys together. 3n plus r, n plus r minus 1, a(n) plus 2n plus r, a(n) plus a(n) minus 2 plus 5a(n) minus 1 x to the n plus r. Okay, so we have that. Now this guy inside here is going to be the guy that we set equal to 0 to get our guy. So here we would have our a(n) times 3n plus r, n plus r minus 1 plus 2n plus r equals minus a(n) minus 2 minus 5a(n) minus 1. And so this would mean that my a(n) is equal to minus a(n) minus 2 plus 5a(n) minus 1 all over, I'd have n plus r times 3n plus 3r minus 3 plus 2. So this looks like the recursive formula here. Is that what you guys got? And also, someone said they were stuck. Did you get stuck anywhere before what you see me having here or after? Okay, but so you got the wrong R values, but what about this expression here? Did you get to this?
The index are a little bit different because the way I shift the index is a little bit different, but basically the same.
Okay, so here for the larger root, that's the one they asked for specifically. So for the larger root, which is R equals a third, you'd plug that in at this point. So this would give you an equals minus an minus 2 plus 5an minus 1 over, this would be n plus a third times, if I plug in a third for R, 3 times R is 1, so I get 1 minus 1, which is 0, and here I would just end up with 3n, which means I can even multiply that 3n, so this can clean up a little bit nicer. And so this would be an minus 2 plus 5an minus 1 over, take this 3, multiply over there, I would get n times 3n plus 1. So that looks a little nicer. So this is the recursion formula for the larger root. And that cleans up nicely, which makes me think that we are on the right track for the most part. So then it asked us, compute A1 and A2 if your A0 is 1. So we're going to assume, so we're going to set A0 equals 1. This means that A1 is going to be equal to, and I'm going to just use this guy right here. So for A1, I would get minus an minus plug in 1 for n everywhere, I get a minus 1 plus 5a0 all over, plug in 1, and I would get 4. Now this is 0 by assumption. Remember, a with a subscript negative, we automatically assume to be 0. And this guy is 1, which is given. So this just becomes a quarter. This also means that A2, this is going to be minus, this is when I plug in 2 for n, this is A0 plus 5 times A, plug in 1 over, plug in 2 for n, this is 2 times 7. So that's going to be minus 1 plus 5 over 4. Yes, this should be 5 over 4 here. Which means that this part here is 25 over 4 over 2 times 7, which I guess you can multiply by 4 over 4. And it just asks for A2, so I'm just going to find that. So this would give us minus 4 plus 25 over 8 times 7. So this is going to be 21 over 8 times 7. And 7 goes into 21 3 times. So this just gives you 3/8. And so we found all the things that they asked us for. Compute the recursion formula for the larger root. Did that. Compute A1 and A2. Did that. So this means A1 equals 5 over 4. And A2 equals 3 over 8. And that problem is done. They didn't ask us to write down the general solution or first few terms of the general solution or anything. It just stops there. Okay.
Why is A negative 1 equal to 0?
This was based on an assumption that we made last class. Whenever we go from negative infinity to infinity with the thingies, I think we did this in advanced.
Oh, the negative infinity to infinity. Oh, I see.
Right. Whenever I make that assumption, we automatically assume that for n less than 0, it's less than 0. So I did that to as a shortcut to make the calculations a little bit nicer. And so I just know whenever I see a negative subscript, I can just assume the thing is 0.
All right.
If they don't, so the good thing about this course is they'll always tell you that there's a singular point. However, in practice, you should always check if something is a singular point or not, right? So if you want to find a series solution at some point, you need to first figure out if that point is or is not a singular point, and is it regular or irregular. So in the class, you'll always be, it'll always be pointed out that you're looking at something that has a singular point. So thankfully, you won't have to figure that out. But in practice, it's not difficult to figure it out. You would just see what x values make this thing 0. And that's how you're going to figure it out. And then you check those limits, and that tells you if it's a regular or irregular singular point. And that's if you're at a value that makes the coefficient of the leading derivative 0. Okay, and that's it. That's all for series. But series, very useful. This is a way that we can numerically solve ODEs. So we looked at solving series solutions with finding series solutions to ODEs at ordinary points, which means these are x series centered at x values that do not make the coefficient of the leading derivative 0. We also saw how to find series solutions using Taylor series. So that's when we have these weird functions like sines or cosines or logarithms as a part of our differential equation. We can just convert those guys to their equivalent Maclaurin series and just use that technique. We now also looked at finding series solution near singular points, which you would realize that if you tried to find the solution using the ordinary points technique, it would not work. Normally, it would just give you the trivial solution, but it won't actually give you the general solution. And I linked to a video in the last lecture where you actually saw someone exploring this. But we're going to move on to a new topic. The main topic of today, Laplace transforms. Yay! Engineers love Laplace transforms. So essentially, a Laplace transform is going to give us the power to solve ODEs in the same way that we can solve polynomial equations, which is, it's crazy when you think about it. But the idea is to use an integral transform in order to transform our equations. Now, where this idea came from is back in Calc 2, when we realized that, hey, there was some integration that was really hard or even impossible for us to actually do. However, if we could replace the function with a power series, we know that that power series is absolutely convergent on some interval, we could do the integral of the series on that interval and get to the answer that way. So we saw also in this class that power series are useful for solving ODEs that have non-constant coefficients that we don't know how to deal with. So the idea is power series are insanely useful, and they're useful all over math. Series is in general a useful thing, not just in calculus, in a calculus sequence of mathematics course, but in mathematics in general and in computer science in general. Series, very important. If you can convert things to series, it's really nice. However, sometimes we want to actually go a little bit more general. You see, a series is something that's called a discrete sum. It adds up things for specific values like n equals 1, n equals 2, n equals 3. The series cannot touch any value in a range. So for example, it's almost nonsensical to talk about a series for n equals pi or for n equals 0.5 or something like that. So we want to generalize the idea of a series. Can we somehow generalize this thing? In the same way that we can take a function and find a power series that represents that function, is there some way to generalize this and maybe take a function and find some sort of integral function that generalizes that function? Because integrals are more general series. An integral is also a way to add up a bunch of things. You might recall this from the Riemann sums definition of an integral. An integral is just a really sophisticated way to sum things up, where you're not just summing things up on integers or discrete values, you're summing things up on all points in some given interval, right? So this leads us to the topic of an integral transform or a transformation. So a function, you tend to think of it as something that takes values and as inputs and output other values. A transform or a transformation is something that takes a function as input and output some other function. We're going to look at integral transforms, right? So we're going to input a function, namely here, the function is f of t. We're going to plug it into this formula with an integral, and the output is going to be some other function, namely that function is going to be called f of s, right? So for a function f of t, we can calculate another function f of s by this kind of formula. This is called an integral transformation. So it's basically a formula that uses an integral to take functions as inputs and output other functions as outputs, right? And as I said, power series are insanely useful and we want to generalize this. So here's how we're going to do it. So here is the general form of a power series. I'm using t because, you know, our variables for differential equations is often going to be t. That's what we're counting. Where a of t comes from some function, right? So there's some function that's giving you the coefficients of your power series. So let's call that function f of t. So I can think of a power series sort of in this way here. And I just set x not equal to 0 just because it's easier to type out stuff. So this is like a general power series, like your an x to the n is the same thing. The idea is I'm just calling it f of t x to the t because I don't just want to count by n, I want to generalize it. So now I don't want to go from t equals 0, 1, 2, 3, etc. I want t to be any real number. So basically I transform the sigma into an integral, right? So I take the same thing and I just think, what if we're an integral here? So I don't have to just add up with discrete values of t. I can add up on any value of t on the interval. So we have this. Then of course in calculus, one thing you learned is that the exponential function y equals e to the x is not only the most important function in calculus, it's kind of the most important function in all of mathematics. So writing things in terms of base e is very useful. So that's the next step. So I'm going to take x to the t, going to write it as e to the ln of x to the t, and then I'm going to bring the t down by the log rule. Now, of course, for the log to be defined, let's make sure that we're not doing complex numbers here. So we're going to assume that our x is greater than 0, for sure. But also, this here, as you'll notice, is an improper integral. And that improper integral involves an exponential function. Exponential functions grow really fast. So pretty much one way that we can try to give this integral the best chance of converging is to make sure that the exponential part is decreasing as opposed to increasing. And so to do that, all I need to do is make sure that my ln x is a negative number, which also gives me the criteria that x should be less than 1. So I know I want my x to be greater than 0 but less than 1. I want it to be greater than 0 to avoid complex numbers, and I want it to be less than 1 to ensure that my ln x is negative, so now I have e to a negative power. So this part of the function is decreasing, and hopefully this function will converge because of that. Now there are other ways that you can come by this kind of generalization by looking at this formula as a geometric series with base x, but I digress. We get here eventually. Now, because I want my log to be negative, what we can do is just set ln of x equal to negative x, where x, s is some positive number, and I get the integral looking like this. And ultimately what we've just done is we've created a very nice integral transform. We are looking at an integral transform of a function f of t that pretty much generalizes a power series. So this is an integral transform that should be analogous to a power series, but it's more powerful than a power series. It's like power series final form, right? So this is actually a very important formula. We call this guy the Laplace transform of a function f of t, right? So you start with a function f of t, you plug it into this formula, the integral from 0 to infinity of that f of t times e to the minus st dt. The assumption is s is a real number that's greater than 0. Once you compute this integral, you'll notice that it is a definite integral. You integrate with respect to t, so the numbers are going to be plugged into t, so your answer is going to be a function of s, which is why this is called big F of s. So this is takes a function of t and it outputs a function of s. So it's a transform, and because it does that transform via integration, it's called an integral transform. This particular integral transform is called the Laplace transform. It's named after a mathematician named Laplace, which you will know has a lot of other things named for him, like the Laplacian, something else that physicists and engineers come across all the time. So this is a continuous generalization of a power series, and it's actually quite useful. There are other notations for it. This fancy L of f of t, and you can specifically identify it as a function of s, or you can leave off the function of s, or you can just call it big fancy LF whenever you're lazy. Everyone will kind of know what you're talking about. So this is Laplace transform. It's very useful. And it turns out it's actually pretty useful in ODEs. But before that, let's actually find some Laplace transform. So this is a theorem that tells you when a Laplace transform will exist. I put it here for completeness. You don't really need to know that formula because whenever I ask you about a Laplace transform, it will exist. So let's actually just talk about finding Laplace transforms. So here are some functions. We're going to go through and we're going to find the Laplace transforms of these functions. So suppose I have a constant function. What would the generalization of the power series of such a function look like? What would, if I have an exponential, what would the generalization of the power series look like? If I have a power function, t to the n, what would the generalization of a power series look like? What would the Laplace transform of each of these look like? So that's what the first part of the game is about, just finding Laplace transforms for individual functions. So what we can do is we can just apply the definition. So here, I would say, well, the Laplace transform of our function f of t here, which I can call big F of s, well, this is going to be equal to the integral from 0 to infinity of f of t times e to the minus st. Now, the definition of a Laplace transform is very important. It's literally in a bunch of double boxes, right? So I boxed the formula and then I boxed the boxing of that formula. So this is a formula that you definitely should know by heart. One of the best ways to memorize a formula is to every time you're using it, just write it out. So that's what I'm doing here. I wrote that out. Now I'm just actually going to plug in the function. The function is a constant. So I will have that. Now k is a constant and this is an integral, so you can actually ignore the constant. S is a constant as far as the integral is concerned because the integral is with respect to t. So the integral of e to a constant times t would be 1 over the constant times e to the t. So this just becomes minus k over s e to the minus st between 0 and infinity. And yes, technically you'd have to do the limit as n approaches infinity and take the limits from 0 to n, but whatever, we're big kids now, we can kind of skip that. Plugging in infinity, so this is, it approaches 0 when you take the limit as you approach infinity. Tons of ways you can see this. One way is to see it by L'Hopital's rule. Gives that when you plug in infinity, you get 0. Why? You have, oh, you don't even need L'Hopital's rule here. Never mind. We'll need it later. because e to the minus t means the exponential goes in the denominator. And so we have a constant in the numerator, and the denominator is a polynomial times an exponential. That's going to go off to 0. Then fundamental theorem of calculus, you subtract this, which now becomes a plus. Now you plug in 0 for t. And then we have pretty much k over s. And so k over s is going to be the answer. So the Laplace transform of a constant is that constant divided by s. So for example, if I ask you, what is the Laplace transform of 2? It's 2 over s. What is the Laplace transform of pi? Well, it's pi over s. What is the Laplace transform of 1/2? Well, it's going to be 1 over 2s, etc. Right? So this is the Laplace transform of a constant. It's just that constant divided by s. Of course, the Laplace transform of 0 is 0. We'll be using that later because that's 0 over s, etc., etc. Okay, so that's it. We can just use this definition to find Laplace transforms for certain functions. This is a nice function. You can think of this somehow as a continuous generalization of the power series of a constant. Yes, s is a constant. S is technically not a constant, it's a variable, but with respect to the integral, it's a constant because the integral is dt. So s is a constant with respect to the integral. Right. Okay, so that's the Laplace transform of a constant. What about the Laplace transform of an exponential? So let's say I have this function. I have an exponential function and I want to find the Laplace transform of that. So again, Laplace transform is going to look like, well, the integral from 0 to infinity of f of t e to the minus st dt. This is going to be the integral from 0 to infinity of e to the at e to the minus st dt. Now this is going to be, I can rewrite this actually. This is e to the minus s minus a t dt. Now it should, let's go one step further before I say the comment I was going to say. So now the integral of this guy is what we want. So this is going to be 1 over the constant times e to the original function between 0 and infinity. Now here's the thing. So this here, this is equal to minus 1 over s minus a times e to the s minus a times t. So now here's the thing. If I'm going to plug in infinity here, it's going to matter whether or not this coefficient of t is going to be positive or negative. Because if I plug in an infinity for t and the coefficient here is positive, then that will go to 0 and that gives me a nice number. However, if I plug in infinity for t and the coefficient here is negative, then that means we keep change flip, we get an infinity in the numerator and it would diverge. So you should notice here for convergence, we actually need something. We need that s minus a must be positive. That is to say that s must be larger than a. So that is also an assumption. S is still a constant with respect to this variable, but a is some other constant, and I just know that this integral will only work for the values of s that are larger than that a. And now what I can do, once I plug in infinity, this guy goes to 0, fundamental theorem of calculus. And once I plug in 0 for t, I just get s minus a. This is just 1 over s minus a. And that's that guy. So what I just showed you is that the Laplace transform of an exponential is just 1 over s minus a. So for example, if I ask you, what is the Laplace transform of e to the 2t, then it's just going to be 1 over s minus 2. What is the Laplace transform of e to the minus 3t? Well, it's just going to be 1 over s plus 3, etc., etc. Is what non-negative? I want it to be strictly, I want the s minus a to be strictly positive. If it's non-negative, this means that I would include the possibility of it being 0, but then I would have to deal with the infinity times 0 scenario in the power of an exponential in the denominator of a fraction. Like, I don't want to do that. Right, it is minus 1 over s minus a, but it's the fundamental theorem of calculus, so you minus the minus. Right? Technically, it's going to be 0 minus a minus 1 over s minus a. Yeah. So we get that. And now we know how to find Laplace transforms of exponentials. What about power functions? So t to the n, where n is some positive integer, right? So like a t squared or a t cubed or etc. Right? I want to find the Laplace transform of such a function. T to some positive integer power. Then I'm going to realize that fs is going to be the integral from 0 to infinity of f of t times e to the minus st dt. This is going to be equal to t to the n e to the minus st dt. And that guy, you would of course realize that you would need integration by parts repeatedly, in fact. So you can do the tabular method, which we learned in Calc 2. So you can draw a table below that, start doing that stuff. Now you'll realize that what's going to start happening eventually. So we're going to keep differentiating the t's. So this here is going to be n times t to the n minus 1. N times n minus 1 times t to the n minus 2, etc. You're going to keep going. Eventually, you're going to exhaust all the powers of t's. And of course, the insightful among you would realize that you will end up with a coefficient of n factorial times t to the 0 at some point. And then the next guy is 0, in which case you stop the process. Over here, you're going to keep integrating the exponential. So you get minus 1 over s e to the minus st. Then you get positive 1 over s squared e to the minus st. Then you would get negative 1 over x cubed e to the minus st, etc. So this is going to go on for a while. And there's going to come a point here where I'm not going to be sure what the sign is because it's going to depend if it's odd or even. And I'm going to have something like 1 over s to the n, because it would have gone n times e to the minus st. And then I integrate once more, and that's going to be e to the minus st over s to the n plus 1. Now you do the tabular method, in which case you're going to multiply across this product. That gets a positive sign, and you're going to be alternating these guys. And you're going to multiply across this. That will get a negative sign. Then you're going to multiply across that. That will give you a positive sign, etc. Now you're going to eventually come down here where you don't know if this is going to be a positive or a negative sign, but we are going to be able to figure out what it is. And then you multiply across here, which is again going to be like a positive or negative sign, which is switching places. Now what you'll notice is that in the first term, according to the tabular method, you add up all these products. So you would get t to the n times a minus e to the minus st times 1 over s, and you apply a positive sign. So this would give you minus t to the n over s e to the minus st. Then you go down to the red. This guy gives you a negative sign. So you have minus nt to the n minus 1 e to the minus st over s squared. The next term would be a negative 1 over s cubed e to the minus st. You apply a positive sign, so it stays negative, and you multiply by this guy. So you still have a negative here. N times n minus 1 t to the n minus 2 e to the minus st over s cubed. You'll notice that we actually don't need to know what these signs end up being, because these guys, the signs on the tabular method and the signs on this guy will always conspire. They'll always be opposites. So you literally always get a negative. So this is also going to be a negative dot, 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 dot. Eventually, you're going to end up down here. Where you would end up with a minus n factorial over s to the n plus 1 e to the minus st. And we have all of that between 0 and infinity. So right here, I'm just using the tabular method, which is a Calc 2 technique. If you don't remember the tabular method, you can watch my 212 videos. I teach this method there. Okay, so now we kind of have this. And at this point, we're going to need L'Hopital's rule. Oh, we're almost at the end. Oh, good. So by L'Hopital's rule, L'Hopital's, all of these guys here are going to go to 0, because I here have infinity times 0 in the first term. This is going to go off to infinity. That's going to go off to 0. And that is going to keep happening. However, the exponential goes to 0 a lot faster than t goes to infinity. You can verify this with L'Hopital's rule. So all of these terms here are going to go off to 0. So this is going to go off to 0. That's going to go off to 0. Everybody go off to 0, except this part here where there is no t. This part here is going to go off to 0 for t approaching infinity. For t approaching infinity. For t approaching infinity. You'll also realize that when you plug in t equals 0, they also go to 0. So and t equals 0. And t equals 0. And t equals 0. Everyone is going to go off to 0 except one term. This guy is 0 as t goes to infinity, but it actually doesn't go to 0. It goes to n factorial minus n factorial over s to the n plus 1 for t equals 0. And so by the fundamental theorem of calculus, we kind of end up with n factorial over s to the n plus 1 is going to be our answer here. So this means that the Laplace transform of some power of t is going to be n factorial over s to the n plus 1. So for example, we can have the Laplace transform of t cubed. Well, that's going to be 3 factorial over s to the 4, etc. Anyway, what I just showed you is us using Laplace transform to figure out the definition. We use the definition of the Laplace transform to figure out the Laplace transforms of various functions. And essentially, we can get to this table. So here, I actually proved this in general. So here they use the 1, and they gave you 1 over s, but I just proved that for any constant, you get a constant over s, assuming, again, s is greater than 0. For e to the minus at, the Laplace transform of that function is 1 over s minus a. I also showed you that. And I also mentioned that your s should be larger than a in order for this to converge, because otherwise the integral would divert to infinity. I just also proved for you that the Laplace transform of t to the n is n factorial over s to the n plus 1 for s greater than 0. We used integration by parts there in the version of the tabular method just to streamline things. But essentially what I just did, the kind of processes I just did, you can essentially derive the Laplace transform of a bunch of functions, but here we just put them in the table because we don't always want you to derive them. So yes, it's possible for me to specifically ask you to derive a Laplace transform for a function, but most of the times we just want you to be able to use a Laplace transform. You just look it up from the table. So you just look up this formula. When it comes to this table, the following formulas here are very important, including 18. You pretty much ignore all the other ones. The other ones will not apply to our syllabus. So formulas 1, 2, 3. So the important guys in this table, the ones you must know. You must know that is true. You must know that. You must know that. You must know that. That. You don't need to know the hyperbolics. You must know this. Although there is a trick for the exponential times these guys. Notice that multiplying by an exponential actually does a shift. Notice that it shifts s to s minus a whenever it occurs. Notice that, right? So for example, you can take a note of this following here. When we looked at e to the at, you can think of this as 1 times e to the at. The Laplace transform of 1 would be 1 over s. Multiplying by e to the at actually shifted the s to s minus a. This property actually holds true in general. Notice that here, if I look at the sine of at Laplace transform versus the exponential times the sine of a constant times t Laplace transform, you'll notice that what happens is that you just took this Laplace transform, and where you saw s, you shifted it to s minus a. So multiplying by an exponential just shifts the Laplace transform. So if you know the Laplace transform of any individual function, then an exponential times that function will just shift the s by the power of that exponential. So that's something you can know in general. What else do we need to know? Yeah, which is what I just said is what's in 14 right here. So an exponential times a function, the Laplace transform of that is just going to be the Laplace transform where the s is shifted to s minus c. Okay, anything else? All of these are nice formulas, and at some point, everyone who uses the Laplace transform uses something in this table, but we're just using what we need. Also, this one is going to be important. This one is the one that's going to help us to solve ODEs. In fact, I think that's one that I actually want to derive for you, because there's actually another formula that personally I prefer to use more than this one. And so I'm going to show you that formula. So another way to look at 18 is this, right? The Laplace transform of the nth derivative of a function can be expressed in this way. You'll notice that it includes the Laplace transform of a lower derivative. So this is kind of a recursive version of 18. And you can just now find Laplace transforms of derivatives of a function recursively. So let's first prove that this is true. Suppose I wanted to find, and I'm just rushing here so I can get to the computational parts. Suppose that I wanted to find the Laplace transform of a derivative, like y to the nth derivative. Then by the Laplace transform formula, this is integral of e0 to infinity of y to the nth derivative times e to the minus st dt. What I would do here is, again, integration by parts. Or I don't need to, I'm not going to do the tabular version because it only takes one step for you to see it. So int by parts with u equals e to the minus st, and then do my dv equals y to the n dt. Then my du is going to be minus s e to the minus st, and my v is going to be one less derivative, so it's n minus 1. And so plugging this in, it's u times v minus the integral, which becomes plus, of v du. And this is 0 to infinity, and here I'm plugging in 0 to infinity. So this is just going to be e to the minus st, y to the n minus first derivative between 0 and infinity, plus I can factor out s because it's a constant as far as the integral is concerned. And we're going to make another assumption here, such that when I plug in infinity into the exponential, compared to the derivative, it's going to decrease to 0 so fast that it makes this whole term decrease to 0. And in fact, there's a theorem that says this is specifically the case in which we can find the Laplace transform of such a thing. It's called Corollary 6.2.2. So your book actually makes the assumption on the derivative in order to prove that this is true. So we're going to make that assumption so that when I plug in infinity for t, this part goes to 0, minus when I plug in 0 for t, this is just going to be y to the n minus 1 derivative evaluated at 0, plus here s. Now when I look at this part here, you'll notice that that is the Laplace transform of y to the n minus first derivative by definition. So this ends up being the Laplace transform of y to the n minus first derivative. And so the Laplace transform of the nth derivative of a function is minus y to the n minus first derivative evaluated at 0 plus s times the Laplace transform of the n minus first derivative, which is as shown above. Now we're going to put this together pretty soon and you're going to see like something amazing happen. So that's how this formula came about. Here's why that's nice. We now know by the above the following. So for example, Laplace transform of y prime is going to be minus y0 plus s times the Laplace transform of y. Laplace transform of y double prime is minus y prime of 0 plus s times the Laplace transform of y prime. Laplace transform of y triple prime is minus y double prime at 0 plus s times the Laplace transform of y double prime, and so on and so forth. So for example, the Laplace transform of a fourth derivative would be minus the third derivative evaluated at 0 plus s times the Laplace transform of the third derivative, etc. So this pretty much goes on recursively. And that's pretty much useful. And this formula is equivalent to this formula. If I just take these recursive definitions and plug it back into the previous one to build up to an original formula, I would get this formula right here. But personally, I like memorizing this formula. And yes, a part of that, I guess, is nostalgia, because when I learned this is the formula that I learned. I didn't learn this version. And so I'm kind of already partial to this. But it's also smaller to remember. And because I hate memorizing stuff, just seeing a longer formula automatically makes my brain just check out. I'm like, nope, not going to remember that. I'd rather remember this. There are only 2 terms to remember here. So now we can have all of these things. So by the way, these are important for you to remember, by the way. In particular, these 2 are important for you to remember. It's very rare, if ever, I'm not going to ask you for a Laplace transform of something higher than a second derivative. And chances are you're not going to be asked that in the departmental final either. So at the very least, you should know those 2. Whew. Okay, so that just shows us how to find Laplace transform of derivatives of functions recursively, which is really cool. Okay, now here is what we were building up to. So we invented, or Laplace invented, a generalization of the power series called the Laplace transform. This allows us to use an integral transform to transform a function into some other function using an integration formula. Here's the upshot. Given an initial value problem, you can actually take the Laplace transform of both sides of the equation and transform the equation in the variable s. And it turns out, if you have a linear ODE, this process will actually transform the ODE into an equation that is not a differential equation. And in fact, if it's linear, it will transform it into a polynomial equation. So Laplace transforms actually give us the power to go from a differential equation to a polynomial equation. And everyone loves polynomials, engineers specifically, which is why they all love Laplace transforms. Engineers that use ODEs in their work, a line of work all the time, a lot of the times, either they're using Laplace transforms or they're programming a Laplace transform, or the calculator they're using is using a Laplace transform, etc. Laplace transforms are very nice because it turns ODEs into polynomial equations whenever the ODE is linear. It's very nice. And another thing that's very nice, you will notice that in this recursive formula, the initial conditions, y of 0, y prime of 0, etc., these guys are all built into the Laplace transform, which means once you actually hit an ODE with a Laplace transform, your initial conditions are built into that process, which means you never have to find an arbitrary constant that will give you that initial condition, because the initial condition will already be there. So before, when we had to solve ODEs, we had to find the C1s and the C2s and the C3s, etc. Here, if you hit something with a Laplace transform, it eliminates the need to find those guys. So once you take an ODE, an initial value problem, you hit it with a Laplace transform, you immediately get to an answer that is the particular solution. You would never have to go through a general solution. Here's the issue, though, if you can call it an issue. Once you hit something with a Laplace transform, it translates all the functions into functions of s's, which means your answer is going to be in like s's, which means you're going to have to need to be able to take a back substitution. This is called the inverse Laplace transform. Basically, for you guys, it's not going to be that bad because you are once again going to be using this table. Basically, if you get an answer that looks like this by using a Laplace transform to evaluate an ODE, you can just either back substitute it and realize that the answer must have been a sine function. So if your answer looks like this, then that means the solution to the ODE is this. This guy here is called the inverse Laplace transform because this guy is called the Laplace transform. And so here, that's why you see that notation here is for inverse Laplace transform. So when you hit something with an inverse Laplace transform, you're going to get expressions that you can match up with guys in the second column here. Then you're going to back substitute to get them to be this column here, and that's going to be your answer. So that's what this second box is explaining. At the end of the day, even with the back substitution, it's often worth it. However, in our class, we are going to be doing ODEs for which you already know how to find the solution to the ODEs by other potentially simpler means. So you're not going to see fully the benefits of it, but the goal is to get you used to the process. So what we're going to do is we're going to do these examples here, examples A, B, C, D. We're going to go through these examples. We're going to use Laplace transforms to get through these examples. And then we are going to, you're going to be able to see the process. Like, how does this all fit together? Because I know, hopefully you understood the calculations I was doing and why I was doing what I was doing, but it's been a mouthful and you're probably lost in seeing how this all ties together. So now I'm going to do an example for you to show you how it ties together. So let's do these examples. So as always, I'm going to do example A for you, and you guys can help me with the others. Okay, so here's how it's going to look. So I see this, I want to use a Laplace transform. Yes, I know you can solve this by other means, but I specifically want you to use a Laplace transform. This is an initial value problem, okay? So what you would do is step one, take Laplace transform of both sides. Now this part I'm going to transform of both sides. Now I'm going to write this in blue because normally you don't write out this, but I want you to see what's actually happening. So you would take the Laplace transform of y double prime plus y equals the Laplace transform of 0. Take the Laplace transform of both sides. This means Laplace transform distributes across sums because its definition is an integral. Basically, this means by taking a Laplace transform of both sides of an equation, it means you can individually take the Laplace transform of each part. We can also factor constants out. Again, because it is an integral. So for example, if there was a 5y here, I could have factored out the 5 and move it over here. We'll see examples of doing that later. So you hit both sides with a Laplace transform. Now here's what you do after that point. You're going to set the Laplace transform of y. You're going to call it something else. Some people call it big L. I will call it big Y. Now, what you can do is you can rewrite the Laplace transforms of everyone else. So Laplace transform of y prime. Again, I'm going to need to find the Laplace transforms of all the derivatives. Since it's a recursive formula, I have to first find the Laplace transform of y prime. This is going to be minus y0 plus s times the Laplace transform of y. This is going to be minus y0. My y0 was 0. Plus s, my Laplace transform of y, I just call that big Y. So this is just s times big Y. Now I can find the Laplace transform of y double prime minus y prime of 0 plus s times the Laplace transform of y prime. Y prime of 0 is 1. So I go here, plug that in. Laplace transform of y prime was s times y. So this is minus 1 plus s squared times big Y. Now, the Laplace transform of 0 is 0. So I found the Laplace transform of everybody. Laplace transform of this guy, I call that big Y. Laplace transform of 0 is 0, so the right side is going to be 0. Laplace transform of y double prime is going to be this guy right here, which I found using the recursive formula. So now, technically this is step 3. Step 2, find Laplace transform of each term. With the derivatives, I use that recursive formula that I proved for you earlier. And with the right side, you just use the table, right? Or you just know how to find the Laplace transform of constant. It's a constant over S. Step 3 now, it's plug into the ODE. No. We proved earlier that the Laplace transform of a constant is a constant over S. This means that the Laplace transform of 0 is 0 over S. Right. So now I go and plug it in. So my Laplace transform of y double prime, I'm going to plug in this expression. Then I have the Laplace transform of y that I called big Y. So I'm going to plug in that expression. Then I have 0 on the right. Laplace transform of that is 0. Now notice what you have here. There are no derivatives in this equation. Gasp. It's an ordinary equation. In fact, it's a polynomial equation. And that is how, using a Laplace transform, you can go from an ODE to a regular E, a regular equation, right? So now, what you want to do is you want to solve for the Laplace transform of y, because then you can do the back substitution to get to the y. Now this, it's just a regular equation. You literally solve it the same way you would if you were an algebra student, right? So you'd factor out the common y, you'd have s squared plus 1 over here. You move that 1 to the other side. And so your y equals 1 over s squared plus 1. And that, by the way, is the solution to the ODE. This guy is the Laplace transform of the solution. It's kind of like when you do a substitution and you found the integral, but your answer is in another variable. The ODE in the variable s. Was there an s that I missed? No, it's an s squared plus 1. There was no s in front of this. Right, Laplace transform of y is just big Y, so that gets replaced with big Y. And then this guy here gets replaced by that. So I have this and that. Y is a common term, so I get s squared plus 1. Now here's what we would notice from the table. So now you need to translate your answer. So that's step, I don't know what step we're in, step 5. If required. There are sometimes, ever so often, where you're not required to translate your answer back to the variable t. You can leave it as a function of s, but that will be indicated in the problem. But here, and now what you realize is, at this point, you would see from the table, so we're going to go to that table. And this table is in your book, by the way. It's table 6.2.1 in the 10th edition. You go to the table, and essentially what you're doing is you want to find something that looks like that. A constant over s squared plus a constant. And you'll notice that this guy looks like that. Rule number 5. So from the table, you're going to realize that that guy seems very relevant. So this here was the Laplace transform of the function. And this here is the function, or you can call it the inverse Laplace transform of the function. And here, a equals 1. Notice that if a equals 1, you would have 1 over s squared plus 1 squared in the right side, which means your solution is sine of 1t. And boom, there's the answer. So you will notice here that There is no C1 and C2s for me to figure out, no general solution, particular solution, homogeneous solution. The initial conditions are built in. Now, of course, we know that if we were to solve this by other means, we'd assume y equals e to the rt. Remember that, we'll get r squared plus 1 equals 0 for the characteristic equation. R would be plus or minus I. We'll get c1 cosine t plus c2 sine t. Then we'd have to find the derivatives. Then we have to plug in the initial conditions. Then we have to set up a system of equations to solve for the C1 and C2. And eventually, you'll realize that the coefficient of the cosine had to be 0. The coefficient of the sine has to be 1. Why isn't it cosine of t? That's a good question. If you go to the cosine of t, you'll notice that in the cosine version, version 6, the numerator actually has s in it. So the cosine comes from there being an s in the numerator, while the sine comes from there being a constant in the numerator. So that's why it's not the cosine. Now, a word of warning here, which I believe I typed this out. Maybe it was here. Finding the inverse Laplace transform means going from the right column in the table to the left column. This means we will have to write the S expressions in very specific forms so that we can convert them back, right? I need to be able to express everything that I see in this answer in a convenient form. I need to think of this as 1 over s squared plus 1 squared. I need to kind of rewrite it in a nice form that fits some term in the right column. Now, here's the thing. Here's one of the drawbacks, and this is just, it gives us something else to ask you to do in an exam, is sometimes you get an answer that doesn't really look like anything in the right side of the table, so it requires you to do some work. Oftentimes that work would involve things like multiplying and dividing by a convenient constant. Sometimes it would involve finding partial fractions or whatever. Sometimes you get this big expression over here that you have to break into smaller expressions to kind of fit it in the table. So that's the only drawback. It's a drawback when you're doing it by hand anyway. Of course, you're not going to do this by Laplace transforms except when it's specifically required of you. But the idea is, even with much more complicated problems where you don't know how to solve it by hand, a Laplace transform will transform such a problem into a polynomial equation, which you can solve. And then you can do that, right? Because polynomials are their own beast as well. I mean, not every polynomial is going to be a walk in the park. But we know how to solve them a lot more, and we have a lot more numerical techniques for them than we do for ODEs. So translating things to a polynomial is often very convenient. Okay, so that was a long-winded explanation of that one. Let me do the second one a little bit quicker, and then maybe I'll have you guys help me with the third one, just so you can see it a little bit more streamlined. So here's a problem, and again, I know you know how to solve this by other means, but let's say the issue was specifically solve this guy via the Laplace transform. Okay, so again, first thing I would do is Laplace transform both sides. I know that's going to just be the Laplace transform of each individual term. So what I'm just going to do is find the Laplace transform of each individual term. So set the Laplace transform of y equals to y. This means the Laplace transform of y prime is equal to minus y of 0 plus s times the Laplace transform of y. Well, that's going to be minus 1 plus s times big Y. This also means that the Laplace transform of y double prime is going to be minus y prime of 0 plus s times the Laplace transform of y prime. That's going to be positive 1 plus s times minus 1 plus s times big Y. And that is going to be 1 minus s plus s squared big Y. Then I'm going to, of course, Laplace transform of 0 is 0. So now I'm going to plug those guys into the ODE. So my y double prime gets replaced by 1 minus s plus s squared y. My y prime gets replaced by minus 1 plus sy. So that's going to become plus 1 minus sy because I'm taking the negative of that. Maybe I should show you that. Maybe let's not skip too many steps here. Okay. So I'm going to plug in the y prime. That's going to be minus 1 plus sy minus 6 times big Y equals 0. So now you'll realize that's a polynomial equation. We can solve that for y. In fact, if I factor out the common y, I would have an s squared. That's this term. Minus s minus 6 equals, now I would have an s here, which when I move over becomes positive. Then here I would have a 1 plus a 1, which when I move over becomes a minus 2. So that takes care of this. It also takes care of the 1 and the 1, and everyone's accounted for, which means I now have my y is equal to s minus 2 over s squared minus s minus 6. Now this is the answer to the ODE, right? The full answer worked out with initial conditions built in, right? So you see, I can get to that very quickly. Now, the thing is, need to match this up to the table. Which means I need to get this to look like something in that table, but nothing in that table looks like this. I know you guys haven't memorized the table yet, but just so you know, nothing in the table looks like that, right? There's no one with a full quadratic in the bottom. We can have a complete square in the bottom, that's allowed. But we also have other things where there are linear terms in the bottom. So I want to make sure that it's not one of those guys either. So the first thing I would do is I would check to see if this factors. So the idea is I want to break this up into smaller chunks. Which means now I'm going to start seeing, well, does the denominator factor or should I be completing the square? And it turns out here that the denominator factors. Okay, so the denominator actually factors. So now I can do a partial fractions. So I'm going to do the cover up method because it's nicer. Cover up method of partial fractions. So I'm going to go to the original. I'm going to cover up the s minus 3, and I'm going to plug in what would have made that 0. So I'm going to plug in s equals 3 after I cover that up. So that would lead me to 1 over 5. Then I'm going to go here, cover up the s plus 2. Then I'm going to plug in what would have made that 0, meaning I'm going to plug in s equals minus 2. Plugging in s equals minus 2 would lead me to minus 4 over, well, minus 5. Those are the partial fractions. So this guy looks like 1/5 times 1 over s minus 3 plus 4/5 times 1 over s plus 2. Now, these guys are useful. That is going to be an e to the 3t. This is going to be an e to the minus 2t. And I already know the C1 and the C2. There is my solution. So, recap, I want to solve an ODE by Laplace transforms. do the iteration formula to figure out the Laplace transforms of all the derivatives. Find the Laplace transforms of the left and right side. Laplace transform of 0 is 0. Then I'm going to plug in all of these guys into that equation. I would get a polynomial equation. The goal is to solve for y. Here I have solved for y. Y is a function of s. I want to go back to the original variable t, which means I need to be able to match it up with the table. Now, in the table, I don't have anything that looks like this. So now I start thinking, can I break this up into smaller chunks? Partial fractions become an obvious way to do that. Hopefully that's obvious. If you're good at Calc 2, that would be obvious. Then I just do the partial fractions. After doing the partial fractions, now I have smaller chunks that are bite size. And those guys I can match up in the table because that looks like an s minus a. So if I go to the table up here, the required formula is going to be that one. The above used this. When I saw the 1 over s minus 3, this was like the 1 over s minus a with a equals 3. So that brought me to e to the 3t. When I saw 1 over s plus 2, this was the same as 1 over s minus a minus 2, which is like a 1 over s minus a with a equals minus 2. This led me to the exponential with minus 2 in the power, etc. Okay, any questions on this one that I went through a lot quicker? Do we see the process? Do we see how we would look at things? Questions at this point? Okay, so at least one person has no questions. All right, so you guys tell me how to attack this one. What do you do? First thing, solve this using Laplace transforms. Okay, Laplace transform on both sides. How do I do that? Right, so we set Laplace transform of y to be big Y. Then we need to find the Laplace transform of y prime. What is that going to be? Right, minus y of 0 plus s times the Laplace transform of y. In this case, that's 0 plus s times big Y, so that's just s times big Y. Then you're going to find the Laplace transform of y double prime. Similar formula, minus y prime of 0 plus s times the Laplace transform of y prime. Y prime of 0 is 1, so this would become minus 1 plus s times sy. So this is minus 1 plus s squared y. Now what? No, plugging in is premature. You're missing something. Right, you need to do the right side. Okay, so the right side, don't forget. I mean, it's always been 0 up until this point, but it's not because I was ignoring it. It's because the Laplace transform is 0 is 0. And in fact, I never really ignored it. I always mentioned that I did consider it. What is the Laplace transform of e to the minus t? Correct. Laplace transform of e to the minus t is going to be 1 over s plus 1. And again, I'm using this formula. Notice that my a is just -1. So that's what that gives me. So now I can plug in everybody. So now I go into the ODE. The ODE becomes y double prime. Is it a y double prime? Yes. Y double prime minus 1 plus s squared big Y. Then we would have minus 2 times y prime. So I'm going to take minus 2 times this, minus 2s y. Then I have 2y. So that's just plus 2 big Y equals this guy, which is 1 over s plus 1. Right, now that's just a polynomial equation. At this point, we know how to deal with this. We knew how to deal with this years ago. So I'm going to factor out the common y, move the guys to the other side, and then my y would be 1 over s plus 1 plus 1 over s squared minus 2s plus 2. And I would do something like, simplify this, multiply by s plus 1 over s plus 1. And so this would be s plus 2. Right, because I would get, when I multiply, take this s plus 1, multiply that, I would get a 1. Multiply this, I get an s plus 1. So I get 1 plus s plus 1, so that's s plus 2. In the denominator, I would have s plus 1 times s squared minus 2s plus 2. And now what? So that is our answer, by the way. So this is the answer in Laplace transform. Let's find the inverse Laplace transform. So again, partial fractions would be what we would think of doing here. So partial fractions. Now again, the cover-up method would work for the s minus 1. So it's going to be something over s plus 1, the s plus 1, and something over s squared minus 2s plus 2. This I can think of as as plus b, that I have to work a little bit to find. But the s plus 1, I can do the same trick. I can cover up the s plus 1 because it's a linear term, plug in what would have made it 0, which would be s equals minus 1. So plugging in a minus 1 for s after I cover that term up, I would have 1 over 3 plus 2 is 5. So I have that. Now we need to find those guys. So this means that if I multiply both sides by the denominator left, s plus 2 is equal to 1/5 s squared plus 2s plus 2 plus as plus b times s plus 1. So this is going to be equal to 1/5 s squared minus 2s. Let's not mix up our s with 5s, hopefully. 2/5s plus 2/5 plus as squared plus as plus bs plus b. And this is going to be equal to, group all the s squares. I would have a s squared. I would have plus 1/5 s squared. That's it. Plus group all the s's. I would have minus 2/5 s. I would have as plus bs. The s shouldn't be there. Plus all the terms without s's. So that's just b plus 2/5. It's the b plus the 2/5. And so this tells us that, because this is s plus 2 over here, this tells us that a plus 1/5 should be 0. It also tells us that a plus b minus 2/5 should be 1. And it also tells us that b plus 2/5 should be 2. So here you get that your a needs to be minus 1/5. Here your b needs to be 3/5. No, not 3/5, no. 2 I can write as 10/5, so it's 7/5. And luckily those guys work here. So if I take minus 1/5 plus 7/5 minus 2/5, come again? 8. Okay, let's try again. So minus 1 plus 8 minus 2, that's 5/5, and I do get 1. So these guys look like the right numbers here. At least they make those guys work. So my a is minus 1/5. So ultimately, my big Y, I can think of it as 1/5 over s. A is minus 1/5. And my b is 8/5. Okay. Does that check out? Were you guys doing the same thing? Okay, cool. All right. So we all got the same. The arithmetic is what we have to worry about now. This reminds me of a meme, but I won't bring it up at this point. Okay, so now we need to make this look like something in the table, which again, these guys over here, the two terms on the right, don't really look like anything in the table until I decided to do something like complete the square. So yeah, you have to remember how to complete the square. This is actually s minus 1 all squared plus 1 squared. Now, we're very close to matching things up with the table. This guy is going to match up with the table very nicely. That's actually just an exponential. That obviously you can see is the particular solution. These guys are going to give me sines and cosines, which is going to be your homogeneous solution, which kind of tells you that if you did it the other way, the characteristic solution would give you complex roots. Anyway, I digress. Let's actually figure this out. Now, this is actually pretty nice. That's in a nice form. That is going to give us like a sine. The cosine, though, that's kind of messed up, or a bit messed up. Why is that messed up? Well, if I go to the table, you would see here in this guy, it's an exponential times a cosine. Now, what's going to happen is notice that in the numerator, we need an s minus a. So not just an s. So what I would do here is I would subtract 1 and add 1. So then I would get 1/5 times 1 over s plus 1 minus 1/5 times s minus 1 over s minus 1 squared plus 1 squared. And then it would give me a minus 1/5, which when I add it to this guy would give me 7/5. Now, if I go back to the table, these guys now give me the answers. So that's 1/5 e to the minus t. This is going to be minus 1/5 cosine, actually. Minus 1/5 e to the t cosine t. This is going to give me plus 7/5 e to the t sine t. By the way, your intuition hopefully tells you that this guy is going to be what your yp was, and this guy here is going to be your yh with C1 and C2 plugged in. So that is our guy. Okay, so this here is a final. I don't know if it's longer than other methods. Like series is pretty long. Like, this is just something you have to get used to in differential equations. What you guys can do is try the last example for tomorrow's class. Tomorrow's class is going to be really interesting. We're going to do some Fourier series. And what I can also do is, so try this for next time. Also, do some more work. Also, for next time, prove so these are kind of needing to, we kind of need these guys to set up Fourier series. You don't need to prove all, but figure out the method. So these are called the product of sum formulas. We're going to be using that tomorrow to figure out stuff. The hint is to use the addition formulas. Okay, so addition formulas, you were beaten to death with those guys over the head in pre-calc and every class since, so that should be very familiar. Product of sum formulas is also something that you would see in a typical pre-calc class. However, usually they get skipped in a pre-calc syllabus for some reason, and we don't talk about them until you need them much later. So here, I just want you to prove those guys. And work on proving these. So knowing how to solve integrals like this is going to be important. Using these formulas are going to help you. You'll notice that a lot of students, when they see the two, a cosine times a cosine, they tend to kind of think integration by parts. You're going to realize that integration by parts actually does not work on these integrals. It's one of those cases where it doesn't work. No matter who you pick as the u and the v, it's just not going to work out. So what you would do is go from the product case to the sum case here, and you can actually solve these integrals. Show that you can actually derive these integrals here. The values of these integrals are going to be very important to the next section. And note, these forms are going to be very important for us to find the values of these integrals. So that's just something for you to do in addition to the Laplace transform problem here. And with that, we will end today. So hopefully that was clear. Yes, it's a bit long, but it's a worthwhile method. The Laplace transform, very cool stuff. It's generalizing a power series. And with this generalization, we can turn ODEs into regular equations. All right, so that is chapter 6. And yeah, this is everything in chapter 6. Fourier series, I want to say, is chapter 10. So this is all we need from chapter 6. We just wanted to look at the Laplace transform and using it to solve ODEs. That's all in our syllabus. That's all that's in our syllabus for chapter 6. So yeah, try these for next time. You can pause so you guys can take a picture. 5, 4, 3, 2, 1. 5, 4, 3, 2, 1. And 5, 4, 3, 2, 1. Okay. Yeah. All right, but we will wrap up there. And that's it for today. Hopefully that was fine. And I guess nothing to talk about. Just try those, the problems that I set up. Make sure that you can actually get through them. And if you have any questions, and of course you can try the homework on Laplace transforms at this point. You do know everything to cover that section. Derive those forms because they're going to be useful in tomorrow's lecture. With that said, I bid you adieu, stay safe, and I will see you in the next one. Ciao.